Let's talk about the periodic table. If you ever look at a periodic table, typically it's a grid with a whole bunch of squares acting on it. I'm assuming that you have seen one by the time you've looked at this video. And I'm going to just look at one of the entries in it. There's typically three things on it: atomic number, elemental symbol, and the atomic mass. Some of them will actually write the name of the atom as well. The one in my classroom doesn't do that, so that's what I was taking it from. So let's first talk about the atomic number. The atomic number identifies the element itself. This ultimately, as we know now, is the number of protons in the nucleus. That is what determines what makes an element an element. So beryllium has 4 protons in the nucleus, and as written here, any atom with only 4 protons in its nucleus is beryllium. Atomic mass, in units of atomic mass units, is the mass of the average beryllium atom. In this particular case, it's the average atom. Now, there are variations of atoms, which we'll talk about on the next page. Also, another way of looking at the atomic mass is that if I have 1 mole of beryllium, its mass is 9.012182 grams. Now, a mole is a word like dozen or score. It's just a number. A dozen means 12. A score means 20. A mole means 6.02 times 10 to the 23rd. It's a huge number, but there it is. Now, so either one of these works. That atomic mass unit and this sort of go hand in hand. But the atomic mass unit is 1/12 of the mass of carbon-12. Carbon-12 is a carbon atom with 12 protons and neutrons total, with 12 nucleons in the nucleus. Now, there are other types of carbon that have different numbers. There's a carbon-13, carbon-14. When the periodic table was first being developed by Mendeleev, it was thought that the periodic table was basically organized by atomic weight. And it was this guy named Harry Moseley who was the one who actually recognized that it was based upon the amount of positive charge inside of it. Harry Moseley was a young and rising star. Actually, he'd been nominated for a Nobel Prize at one point. Well, more specifically, he was nominated for a Nobel Prize in 1915. And the rule is that if they start looking at the application while the person is still alive, they will consider it, and that is pretty much the only way that you can get the Nobel Prize posthumously. Unfortunately, he was killed before they really started looking at the nominations in any seriousness, and so therefore he no longer became eligible. But he was killed at Gallipoli, which was unfortunate. Now, what he would have been ultimately gotten the Nobel Prize for is developing a technique in order to actually determine what elements are involved based upon X-ray diffraction, as opposed to the chemical properties, which was tradition up till then. And there were a couple other people who used a similar technique who actually did end up getting Nobel Prizes within the next decade after that. So the mass of a proton is about 1.626219 times 10 to the negative 27th kilograms. Now, it does seem tiny. Well, again, protons are tiny. Mass of a neutron, which is the other thing in the nucleus, also has very, very similar mass. There is a slight difference there once you get down to here. But the atomic mass unit is roughly the mass of the proton, which is roughly the mass of the neutron. And if I sort of flash back over here, the atomic mass unit is written right there. So I got 1.66 times 10 to the negative 27th, and these are 1.67 times 10 to the negative 27th. And so if I look at the atomic mass, I have a decent approximation of the number of protons and neutrons. So in case of beryllium, the atomic mass is 9.012182. So I would expect there to be, on a typical beryllium atom, there'd be 9 nucleons. Since beryllium has to have 4 protons, because its atomic number is 4, and there's 9 nucleons, well, nucleons are either protons or neutrons, and so if 4 of them are protons, that means 5 of them have to be neutrons. And when neutral, there's 4 electrons also. The number of electrons matches the number of protons, so they have the same, because they have the same but opposite charges. And this is not a Newton's law thing, it's just the way nature seems to be working. Now, one of the reasons why beryllium does not have an atomic mass of 9 more directly is, one, the atomic mass unit is slightly off of the mass of the protons and neutrons, but also the number of neutrons that are in an atom can vary, just so long as the number of protons. Again, beryllium has 4 protons, typically 5 neutrons, but it doesn't have to have 5. And that's what we get to right here. Let's take example hydrogen, which has an atomic mass of 1.00794 atomic mass units. And usually there's just 1 nucleon if you round that off. It rounds off to 1 nucleon, and that's the proton. However, you can find hydrogens with 2 nucleons, that's known as deuterium, or 3 nucleons, known as tritium. And if you've ever heard the term heavy water, that is, normally it's water is 2 hydrogens and an oxygen that are combined, but if the hydrogens happen to have 2 nucleons, deuterium, then it's known as heavy water. Also notice the notation I have here, that deuterium, I write H with a 2 plus. H I already know has 1 proton in it. This tells me the number of nucleons. These are known as isotopes of hydrogen. And so the isotope in general are atoms, the same element, so the same number of protons, but different number of nucleons. So carbon-12, which is the traditional one, carbon has 6 protons. Carbon-12 would have 6 neutrons, because 6 plus 6 is 12. Carbon-13 has 6 protons because it's carbon and it has to have the same number of protons, but 13 nucleons, which means 7 of them are neutrons. But typically, if you just write carbon, it's understood to be just the typical carbon of, say, carbon-12. Now, if you look at the periodic table, basically it kind of looks something like that. And then there's usually 2 lines down here. As you are moving to the right, so if I take a particular row and I move to the right, we're getting more and more protons inside the atom, inside the nucleus of the atom. We're getting more and more protons inside the nucleus of the atom. The more protons you get, remember protons are positively charged, electrons are negatively charged, and so if I have more protons, more electrons, there's greater attraction here. And so as you move to the right, the size of the atom gets smaller and smaller. Not tiny, no, they start out tiny, relatively speaking. I mean, start this and then just, that's still dropping off way too fast. Something like that. Now, when you move down the periodic table, what's happening is you're adding an additional shell to it. And this is part of the Bohr model, the fact that the electrons act or exist in shells. And each time you add a shell, you add another layer. So if that's my nucleus right there, and this is not to scale, then I have a shell right here for the first one. So this is where the electrons tend to hang out for the first row. And the second row, they tend to hang out here. And so there's this kind of, imagine a gap in between here. Now this is not completely empty space. There's radiation shooting back and forth. But there's a gap between this, and it's possible to calculate, not for physics 110, but physics 151 and 251. You have the math background in order to be able to calculate this. And then the next shell, so this would be, say, the first row, second row, third row, fourth row, fifth row. And as you move out, as you move down, you move out to a new shell where more electrons will hang out. Now it is the actual, if you get into the math of it and get into the detail of it, it does become a lot more complicated than the way I'm presenting it here. But this is sort of the general explanation for why, as you move down, they get larger. So the smallest atoms would be the ones over here, smallest in size. So we're talking about when I say the atom, we're talking about the nucleus plus the electron cloud, as it's generally called. And the largest atoms would be down here.